Okay, we'll get started. So I want to talk about, we're continuing on singular value decomposition. We'll do that also the next 2 lectures, Monday and Wednesday next week. So we already saw what it is, but I'm going to recap a little bit, but go on a little bit, right? So we just showed that every matrix can be decomposed into a sum like that, where the ut and vt are vectors. The vt are orthonormal. So we always had this sigma t ut vt transpose. So remember that this is an outer product ut. They're both column vectors ut. This is vt transpose. So each of them is a matrix. It's a decomposition into rank 1 matrices. The sigma t is always non-negative. Actually, we assume it's positive. We don't write the zeros. Okay. Now, this slide I want to illustrate lots of uses of just the fact that the vt are orthonormal. So far we already have that the vt are orthonormal. That's what I will assume, but later we'll show that the ut are orthonormal too. Now the vt are orthonormal by definition, because we said by definition, because we said v2 is the maximizing vector perpendicular to v1. So they are orthonormal, right? ut are not by definition, because they were defined as ut equals a times vt divided by the length. So there's no reason, no immediate reason why ut should be orthonormal. So we will have to prove that. But even the fact that vt are orthonormal, we'll be able to use. I'll show you some context, and some context I'll just mention, right? So, I mean, we just sort of worked this out, but this is a bit of a recap. AA transpose. I want to tell you what it is. I mean, it comes out to be that. On the face of it, there are r terms here, r terms there. That will be a total of r squared terms when I multiply out. But, of course, the non-identical terms cancel out. So let me just write one more step here in the middle. So I'm going to multiply them out. So that's T1, T2 going from 1 to R. Sigma T1, sigma T2. I will get UT1, VT1 transpose, VT2, UT2 transpose. Okay. So these don't necessarily commute. They are matrices, so you have to write them in order, except you notice that this is a scalar. Right? So this is a dot product, so it's a scalar. So that, of course, can be brought out or whatever you want to do with it. This is 0, again, if T1 is not equal to T2. And I put a word of caution that if instead of inner product you had an outer product, that's not true, right? So we saw that last time. So these all go out if T1 is not equal to T2. Only T1 equals T2 counts. So only the cross terms go away, and then you get that, right? So this we saw. I'll show you something new, but in a minute. We also saw that if A is invertible, then R equals the full dimension is D. So all the sigma t's are non-zero. And the inverse of it is 1 over sigma t Vt ut transpose. I have to show you that is the inverse. So we take A times that matrix and show that that's the identity. Vt ut transpose. And I want to show that this is the identity. That's enough, right, to show that that's the inverse. So you just write expand A. Again, you put T1, sigma T1, UT1, VT1 transpose. It's really the same thing, 1 over sigma T. And here you just have VT2, UT2 transpose. And again, you expand these two, but this times this is 0. Okay, and that's again inner product, right? So this times that is 0 once you expand it out, right? So we just expand it out like we did this. And so this is the identity. So you get, sorry, excuse me, I'm not done yet. I should have just complete this picture. So that's equal to UT transpose over all T. And that's just the identity written to the basis UT, right? So change of basis. So the way you sort of see that this is identity is if I hit it with any x, well, expand x on this basis and you'll get x back. Okay? So you do have to do this little calculation. So I could take any set of full orthonormal vectors, full set of orthonormal vectors, and UT transpose summed over this is the identity. Okay? So the normal identity is when UTs are all the unit vectors. Okay. A may not have an inverse, and often this pseudo-inverse is quite useful. If A is singular, it always has the pseudo-inverse. Again, I only wrote this for sigma t's that are not 0. I wrote it only for sigma t's not 0, so I can take 1 over sigma t, and I've just transposed it. I put VT UT transpose, just like you do for the inverse, right? There's a transpose involved. So if again, I'm going to check by multiplication. I multiply A with that, right? Cross terms go away. Sigma t times 1 minus 1 over sigma t is 1, and you just get UT transpose. This is the identity, but not on all of space, right? So again, maybe it's worth saying, pointing that out. So now we have UT transpose. These are orthonormal, but not a full set. R is less than the matrix UT, by the way, was on that side. So it's n by 1. Matrix is 1 by n. Okay, R is less than n. So this acting on an x equal to 0 if x is orthogonal to the span of the UTs. So if I have something orthogonal to all the UTs, it's 0, right? Because it makes a 0 dot product, right? And it's the identity on the span of the UTs. And that that's just a proof you have to write down, right? So it is identity, but on a subspace. Okay. Now, so in linear algebra, probably you have all seen spectral decomposition. So any symmetric matrix, any Hermitian matrix can be written as sum of t equals 1 to r lambda t. Lambda t are the eigenvalues. They don't have to be positive. Lambda t ut transpose, where the UTs are orthonormal now, right? So eigenvectors which are orthogonal. Okay, so you can write it that. So this is spectral decomposition. We can prove that with one assumption from SVD. That's this simple proof. So suppose you look at matrices, symmetric matrices A, and I do SVD. I don't do spectral decomposition. I want to get spectral decomposition from SVD. So I do SVD, and A's SVD is t equals 1 to r sigma t ut vt transpose, let's say. Okay. I assume the SVD had no ties. Okay. That's a case I can prove very easily spectral decomposition from SVD in these two steps. Now, I cannot assume no ties. There can be plus minus 1 ties. So what that no ties says is, okay, there exists a unique pair of vectors v1 minus v1 such that AV is maximized by them, right? Argmax, whatever, over length of v is equal to 1. This is how we define the first singular vector, best fit line, right? So that's equal to v1 or minus v1. So I cannot avoid having 2 of them. I can always put a negative sign, that's all right. But I will say by no ties that informally that there are only plus minus. Okay? So if that's the case, we have a proof, right? So because A is equal to A transpose symmetric, so that implies A is also equal to sigma t Vt ut transpose. So I've taken that and transposed it. So Vt came to the front and ut transpose, right? no ties implies that we said V1 was unique. Here we've got a U1. The length is the same, right? It's the length of, okay, maybe I should have made that remark. Well, we know that. For any vector x, when I hit it with x, the length will be the same. Therefore, this U1 also should be a max. So U1 better be plus or minus V1. Okay. So we have to pause for a moment. We can make a mistake here, right? We can say no ties means U1 must be equal to V1. So that is not necessarily true. If U1 were equal to V1 always, all the eigenvalues will be positive because all the singular values are positive, right? So this actually says the eigenvalues are plus or minus the singular values for symmetric matrices, right? They're already real. The eigenvalues of symmetric matrices are always already real. But it says they're plus or minus the singular values. Okay? So this proves that you can get spectral decomposition of a symmetric matrix. Now, spectral decomposition of a symmetric matrix is useful, and I'm going to mention two important examples in a minute. It's useful for a lot of contexts, actually. So let's take a high power of the matrix S. I claim that is just, this is symmetric now, right? It's spectral decomposition. I'm going to take a high power. I mean, it better be at least square before I take powers. Rectangular matrices, I can't take powers. But if I take a high power, then only the eigenvalues get powered. The eigenvectors remain the same, right? We can see that by just multiplying out. So maybe since I have not so many slides, I can do all these calculations. So a to the s is sum over T1 equals 1 to R lambda T1 U T1 U T1 transpose, then you have T2 and so on. I could expand this out. I mean, you could also prove it by induction. There are S brackets like that. So T1 through Ts, I get lambda T1, lambda T2, lambda Ts. Now, this thing becomes UT1, UT1 transpose. Then you get a T2. Then you get a T3. But these are all scalars. They're all inner products, right? So they commute, they come out, and so on and so forth. But they're all zero. I mean, sorry. One of them is zero, everything is zero. So you better have T1 equals T2 equals T3 equals Ts. Otherwise, at least one of, if even one pair differs, it's zero. Dot product is zero, so the whole thing is zero. So you only get terms where they are all equal, so that becomes just sum over T, lambda T to the S, UT transpose. Of course, you knew that the eigenvalues of powers of matrices or powers, you also knew that the eigenvectors are the same, right? If AV is equal to lambda V, A to the SV is also equal to lambda to the SV. So you knew that, but this is just saying that by expanding. Okay. But now I want to say something non-trivial. And again, that's extremely useful. So let's see why that's true. Okay, so I want to claim that if lambda 1 is the unique eigenvalue with the greatest absolute value, so in words, lambda 1 is the unique eigenvalue with greatest magnitude. So no ties, no multiple eigenvalues with the highest absolute value. Okay? You could have that for a matrix, right? We are assuming that that is not the case. For instance, if you had the identity, all the eigenvalues have the same absolute value 1, right? So I'm ruling out such matrices. So you take only matrices where lambda 1, and I called it lambda 1. It could have been any lambda, but I can rename it lambda 1, right? So maybe I should, it's worth writing, can be any lambda. T rename lambda 1. Rename as lambda 1. then we want to claim basically that the limit as you raise it to a power with some scaling becomes rank 1. And that rank 1 vector is the top eigenvector, right? So that is important. So why is that? That's just an obvious calculation. So now a to the s, and I'm going to divide by 1 over lambda 1 to the s. Absolute value is sum over t equals 1 to r. I erased, well, I wrote it down there. Lambda t to the s over lambda 1 to the s, right? And we get a to the s. Okay, so the lambda 1 to the s term, sorry, ut transpose. Okay, and then the lambda 1 term in the limit as s goes to infinity, the lambda 1 term becomes u1 transpose. The other terms go to 0 because lambda t to the s over lambda 1 to the s goes to 0 because the absolute value is less, right? Okay, so the other terms go away. Only one term remains. Okay, and we will see a little later today or the next lecture the power method, which is actually just a method for computing. So you can ask, how do you compute singular values and singular vectors? We saw the greedy algorithm, which said if I can compute the best fit line, I can find the best fit two-dimensional subspace, three-dimensional, and so on. But how do I find the best fit line, right? Best fit line is the top singular vector. How do I find it? This is how I find it. Okay. Provided the matrix is symmetric, I can just take powers of it, and sooner or later I'll get pretty close to the top singular vector. Not quite the vector, right? But I get u1 transpose. It's easy to see that if I gave you u1 transpose, you can figure out u1. Okay. So the power method is a way of, in principle, finding the top singular vector. In principle, doing the whole SVD algorithmically, right? I say in principle because some of you know already, but I mean, there's a whole subject of numerical analysis, which has developed beautiful, complicated algorithms. But power method is in principle the starting point. You wouldn't actually implement that, but it's a starting point. Okay, very good. So this was under this assumption. This may not hold. And so we will state at the end of this lecture or the next lecture, we will state, okay, so there's one thing I should back off a little bit. In numerical analysis, usually you see the power method and everything isn't stated in terms of the gap between lambda 1 and lambda 2. We don't want to say that because we want absolute theorems. So I will tell you an absolute theorem whether or not there's a gap. Okay. I mean, it's not new or anything, but that's not the way it's formulated in numerical analysis. So we would like a theorem that holds for all matrices, and we will state that. But at the moment, I assume some strict gap exists between lambda 1 and lambda 2. Then it's true that I get to a rank 1. If it's not true, I mean, if lambda 1 and lambda 2 are equal, you won't necessarily get rank 1. You can get two terms here. Right? Okay, good. So, but that's also used, which is not a subject, but since we have too few slides, maybe I'll spend 2 minutes on this. This little fact is also used for Markov chains. Now, again, I won't actually prove things there, but the point is this. In Markov chains, you have, let's say, n states. You start with an initial probability vector P0. So P0i is the initial probability of being in state I. Okay. And Markov chains, what happens, the probability is just transformed linearly. So the next time around, this is time 1. P1, excuse me, these are row vectors. P1 is just P0 times the transition probability matrix P. This is called transition probability matrix. I won't tell you what this is. It's not my intention to go over Markov chains, so I'm not going to tell you what it is. All I'm going to tell you is that the t step, what happens at time t, the probabilities are just p naught times p raised to the power t. Excuse me, let me use s. I've used s for powers. This is at time s. Okay. And the big theorem in Markov chains is if you run it forever, under some conditions, but if you run it forever, you get to stationary probabilities, some steady state probabilities, which are limiting probabilities. So we want to say this converges to a limiting probabilities. Again, it's not my intention to prove it in detail, but I just want to tell you how that what we have there works to prove that. So what happens for Markov chains is that lambda 1 of p is 1, and everybody else is greater. It's not always true for every chain, but we assume this now. Then we see from there p to the s divided by lambda 1 to the s, but this is just 1. Sorry. Lambda 1 is 1 exactly, not absolute value. Okay. So this is just 1 that's equal to p to the s, and that converges to just some top eigenvector, rank 1 matrix. And now if you hit it with p naught, so p naught times p to the s converges to p naught. This is a dot product, row vector and column vector, u1 transpose. Right? What that says is whatever p naught is, it doesn't matter. I always converge to probabilities proportional to u1. Okay? This is just a scalar. Right? So always converge to probabilities proportional to u1. Right? One fixed u1, whatever p naught is. So maybe that's worth writing, and then we can, whatever p naught is, we converge to probabilities proportional to u1. And these are called the stationary probabilities. So, yeah. Yeah. So I'm doing it, good point, I'm doing it only for p symmetric. Thank you. So you do have to otherwise symmetrize it. So p is symmetric. Yeah. So this is not valid if it's not symmetric. Yeah. Thanks. So you can say, I mean, Markov chains is not the subject of this talk. All I'm saying is it's just a matrix. It's just a matrix equation or whatever. Okay, later we'll see power method. We won't see Markov chains. Okay, now I want to prove. So that's okay. That slide was on just using orthogonality of singular vectors. It's essentially like you would use orthogonality of eigenvectors for spectral decomposition. There are a lot of uses, and here are some of them. Right? Okay. So now I want to prove that SVD actually is not just. We did see that it's best in some sense, but I'm going to prove that it's best in another sense. So we want to define. Here's a rank K matrix, AK. AK is defined as the sum of the first K terms alone of the SVD. This is often called the truncated SVD. So if you go to MATLAB or something like that, there's always codes for finding the truncated SVD. So that takes only the top K terms. So sigma 1 was the highest, remember, and so on. The top K terms, top K singular values and singular vectors, will show that for each K, AK is the best approximation to A of rank K. We want to show that. It sounds very much like what we said already, that VK is the best fit subspace. In fact, it uses that. It is more or less that. but we'll prove that this is true. Okay. So for this reason, in a lot of computations, if you want to reduce the rank of A and still get something decent, a decent approximation, you use the SVD, right? It is the best possible approximation. So this is, in a sense, the reason SVD is used a lot. This and an analog of this we'll prove also for the spectral normal a little later. So, so this proof first, right? First, the rows of A are projections of the corresponding rows of A into Vk, the space spanned by V1 through Vk, I want to say. We saw this capital Vk yesterday, and also these are the singular vectors, right? These are the right singular vectors. Throughout this talk, I'll use U and V for the right, U for the left, V for the right singular vectors. So first we want to prove this. Okay, so, and this is just some simple calculation for, so if I take any vector A, the projection of A onto Vk. So Vk, capital Vk is a subspace spanned by these vectors. And these are a basis because they are orthonormal, right? They're all Vk, so that's a basis. So you take its dot product projection on each basis vector and add them up. That is the projection onto the whole space. So that's for one particular vector A. Now projecting each row of A into Vk, we get this. Okay, and this is just also equal to Ak, that quantity, right? So I want to say that these two are equal. I just do, I just see why it is the case. So I missed one step there. It's probably, I mean, just in between the first and the second equation, there's one step. Which is just that I equals 1 to k. I'm going to write out A, right? A is T equals 1 to R sigma T ut Vt transpose. That's A. And then I have another Vi transpose. And again, this is a dot product. It's 0 unless T equals I. So you get, if T equals I, it's 1 because length 1. This product is the length of Vt if T equals I. Or T equals I, and then you get the next step, and that's Ak. Okay. Okay. Theorem for any matrix B of rank K, this is true. That says that Ak is the best rank K approximation, right? Because whatever matrix I take, the error is less for Ak than for B, less than or equal to. So the proof, take B that minimizes that among all rank K or less matrices. Okay, I don't have to keep saying it, but this minimum exists, right? Again, the set of rank K matrices looks unbounded, but it's not. So you have to convince yourself with that. Sorry, you have to convince. Oops. Okay. You have to convince yourself that minimum exists, but it does. So to see that. First, we argue that each row of B is a projection of the corresponding row of A into the subspace V spanned by the rows of V, right? So I want to claim this. And the proof is, if that's not the case, so if a row of B had a component which is not equal to the projection on the corresponding space of V, we can instead replace it by that, replace that row by the row of A projected onto V. Okay, that replacement doesn't increase the dimension because that's still in the space of V. Therefore, the rank of V doesn't go up. Rank of B doesn't go up. That's important. We are still dealing with a rank K matrix. But I reduced A minus B squared because I now made that row projection of this row onto the space. Originally, it wasn't. So again, this was a row of A. This is the subspace V, right? And my B was somewhere here. Instead, I made it this. And this is the best you can do, right? This is the least. It's a perpendicular distance to V. Okay, there used to be some other point in V, but I made it the perpendicular one. So that's the best. So that reduces, strictly reduces, because I had a component, strictly reduces A minus B, which is a contradiction to the assumption that A minus, this means contradiction, right? So that means A minus B is the best. We started with A minus B best, so we cannot reduce it. So that proves this theorem. Okay. I'm sorry, it's not, doesn't prove yet. Okay, so one more step. So A minus B squared is the sum of squared distances of A to V, right? So B were all projections of the rows of A. So it's the perpendicular distance of the rows of A, which are data points to V. So so among all vector spaces of dimension k, Vk is the one that minimizes that, and that's spanned by Ak. So we get that. Okay. This is from our old theorem that we had, main theorem we had, that the greedy algorithm works. Okay. Now, it's also true for spectral norm. We'll prove that. That is a little more work. It's not. It's a little less obvious, but it's also true. It's also true for spectral norm. It's actually true for somewhat more general class of norms, but certainly for these two important ones, Frobenius and spectral. Okay. So that's a nice thing about SVD. Not only that greedy works, but it's the best approximation in the two norms that you're interested in, when the error is measured in the two norms that are most interesting. Okay. So this will come a little later in today's lecture. Okay, so now I want to, for that, I need also that the left singular vectors are orthogonal. So I must prove the UIs are orthogonal. Again, the right singular vectors were orthogonal by definition because I said V2 is orthogonal to V1, but U's, that's not necessarily true. So we have to prove this. So this is a variational argument. In a sense, you can use this argument also to prove the main theorem, but it's this kind of argument, but we'll prove this here now. So it's a variational argument that says if something is violated, if they were not orthogonal, I can improve matters a little bit. Okay. So let's go back one step. In the case of V's, right, if V1 and V2 were not orthogonal, that's they make a dot product, then I can improve V1 by adding a little bit of V2 into it. That's the kind of argument we are going to see now, but for the U's, because the V's were already orthogonal. Suppose they are not orthogonal. Take the smallest integer such that ui is not orthogonal to some other uj. Okay. So ui, now we want to assume that actually they make a positive dot product. I just assumed they were not orthogonal, but it may be that they make a negative dot product. But then what do? I want to really assume they make a positive dot product for the argument. So why is that? Why is it that I can assume that? What if they made a negative? Yeah, just a negative. So yeah, replace it by the negative of, right? If this was replace ui or uj by its negative, that's still a singular vector. So we may assume that. We also have that j must be greater than I. That's because I was the smallest to violate orthogonality with anybody. So it cannot be violating it with the earlier ones, because the earlier ones were all right. Okay? Must be the later ones it's violating, is it? So j must be greater than I. So here's the variational argument, right? So I take the right singular vector vi, okay, and I'm going to perturb it slightly. Epsilon here is infinitesimal. Okay, so I'm going to assume epsilon is infinitesimal. So second order terms can be thrown out. So I'm going to take vi and add a little bit of vj to it. So I might have said it wrong earlier, but this is correct. That's ui and uj are not orthogonal. I'm going to add a little bit of vj to vi. I added that. I must make the length 1, so I do that. So this thing has length 1 now. And I'm going to show you vi prime is better than vi, which is a contradiction. Vi was the best fit orthogonal to some other things. I'm going to show you vi prime is a better fit, and that can't be, right? So a vi prime, let's see what it is. A vi was a singular vector, so a vi is sigma I ui, right? If it was an eigenvector, a vi would be lambda I vi, singular vector sigma I ui. And then similarly, this you get epsilon, sigma j uj. If you're looking at the book, some of these indices are wrong there, but I corrected them. Now the length of this is length 1, but these two are orthogonal, Vi and Vj, right? They're already orthogonal. So the length is just Pythagoras, 1 plus epsilon squared, but square root. It's important that I have only epsilon squared, only a second order term here. If I had a first order term, this wouldn't work. So these are being already orthogonal is what gives me the second order term there. Okay. So a Vi prime, I'm going to prove is a better fit than Vi, so it is long. So I want to say its length is high. This is a vector, its length is high, I want to say. Well, it's at least as high as the component along Ui, right? Ui is a unit vector, so if I take the dot product of Ui and this, I get something. Certainly the length of this is at least that much. It has other components perhaps, so it's at least a component along Ui. So you take a dot product here, you get Ui transpose, they're still wrong. That's Ui, sorry, that's not U1, that was Ui there. So that's Ui, this should be Ui. I'll correct that before we put it, that should be Ui. So we get sigma I, Ui transpose Ui is length 1, so you get sigma I. Okay. And this is epsilon sigma I Uj, epsilon, this is still Uj, that's still Ui, sorry. So Ui transpose Ui is 1, so you get sigma I. Ui transpose Uj is delta, so you get delta, epsilon sigma I delta. And this I've written, let's see, square root of, I think that's just absolutely true, right? So I get 1 over 1 plus epsilon squared times 1 minus epsilon squared over 2 is less than 1, right? Yeah, I think if you square this, you get 1 plus epsilon squared, you get 1 minus epsilon squared, but plus something. Yeah. I hope I didn't make a mistake. So, no, minus epsilon squared plus epsilon to the 4th over 4. Yeah. 1 minus. It's not quite right. So, but I may have not made a thing. But anyway, it's a second order term. Okay. So epsilon is infinitesimal. 1 over square root of 1 plus epsilon squared is second order. Only second order terms come. If I do a Taylor expansion of that, if I didn't do that right thing, that's equal to 1 plus order epsilon squared. 1 minus order epsilon squared. Doesn't matter what the constant is. Okay, so I multiply this out. I get, most important, I get a first order term here. The rest are second order terms. But the first order term is positive, right? That's all I care about. The first order term is positive. Okay, and therefore I get something greater than sigma I. So that was greater than sigma I there. So all I care about is that these two were orthogonal. So the denominator was second order, and the first order term is still positive coefficient. Well, no, as the epsilon is infinitesimal. So delta was, okay, so delta is not infinitesimal because u's are fixed. So I have ui transpose e, I assumed it's positive. It's a fixed positive quantity, and epsilon is much smaller than delta I choose. Okay. So this is a variation argument, right? Variation argument just means this, that you had an infinitesimal and show that something is violated, right? Assuming ui's are unit length, but they were normalized to length 1. So ui was defined as AVI divided by length of AVI. So they are already unit length. Okay. So so this says that we got something greater than sigma I for the length of this vector. Now, this is a contradiction because Vi plus epsilon Vj. So is orthogonal to the previous V. So remember, Vi was the best orthogonal to the previous ones. I produce something which is better, but I must say also that it's orthogonal to the previous ones to get a contradiction, right? So it is orthogonal to the previous ones since j is greater than I. So Vi and Vj were both orthogonal to all of these. Therefore, the sum is. Okay? So I needed that Vi and Vj are both orthogonal to the previous one. And sigma I is defined with the maximum over all such vectors, so that's a contradiction. Okay? So the UIs are orthogonal. Okay? So I'm going to use that, but I need one more lemma. I'm still trying to prove AK is the best fit in spectral norm. I'm not there yet. I need one more lemma. So I need to prove that A minus AK spectral norm now is just the next singular vector, singular value. Okay? And the proof of this so let me step back a step. This lecture is probably the most technical because I have a lot of details to work out. Maybe I should tell you the agenda just to take a break from this, and then we'll do this calculation. So what will happen after this in the next few lectures, including possibly today, some of it, is we'll see the power method with an absolute theorem, absolute meaning no gap assumptions. Possible today, possibly not. And then we will see how SVD helps us learn a mixture of two Gaussians. So I introduce Gaussian mixtures, and I'll redefine them. But it helps us learn a mixture, K Gaussian, any number of Gaussians. But they are spherical Gaussians only for this. And this is, in a way, a clustering problem. We saw that. We'll also see that SVD leads to what's called spectral clustering. Now, this is in chapter 7 of the book, not this chapter. So spectral clustering is a very widely used technique for clustering. Not just mixtures, so this is also spectral clustering. So first we do it for Gaussian mixtures, then we'll do it a little more generally. Okay? That's a rough agenda, right? For what follows. I may preview the power method at least today. I don't have slides, but I'll preview the power method, and then we'll come back and continue with that and do these things. There's one topic I did not mention, and we'll do it if there's time, which is that length squared sampling to compute SVD. This is in a different chapter as well. I think it's chapter 6 or 8. So the gist of this is that if you want to do SVD of a big matrix, you can do length squared sampling to pick some rows and just do SVD of that rectangular matrix consisting of those rows. That gives you a good approximation, provable approximation, right, for any matrix. So the gist of this is SVD on length squared sample rows. Gives you a guarantee on what the error is. I may permute these topics so that I do perhaps this before that. But we'll certainly do the power method and Gaussian mixtures, spherical Gaussian mixtures first. Okay, so that is a relief from the technical detail, but now we'll go back to the technical detail. So, oh, I see, I had edited that, but I apparently didn't come. Okay, so I want to prove that A minus AK, spectral norm is just sigma k. So SVD is that. A minus AK. So AK subtracted out of the first k terms. So I go k plus 1 to r. So I want to prove that the spectral norm of this is not very bad, is equal to that thing. So let V be the top singular vector of that. Spectral norm is defined by V, of course, right? So we can express V as a linear combination of V1 through VR. So why is that? So V was the top singular vector of A minus AK, okay, which is these things, right? In fact, it's even true that it's expressed as a combination. I should have said, you don't need to use V1 through all of VR, right? What V T's, what V sub i's is V a combination of. I mean, it's a top singular vector of this matrix, right? So you'll only involve Vk plus 1 through Vr. Anything else is useless, right? Anything else is a waste, right? If I put something other than these V's, I'm wasting length and getting nothing, getting 0, right? So I'll only put that. But here I put all R's, I think. But anyway, you get this calculation. So now you do that. So I put all R's, although, again, very soon it comes down to that. So all, again, the same thing, that Vi transpose Vj is 0 unless I equals j. And so I only goes this k plus 1 to r. J also only goes that much. And those go away. That inner product is a length 1. And so you get sigma I, Ci, sorry, that was the C's from there. And you get this. Right? These are orthonormal, so length squared is just the sum of squares. That's just Pythagoras. Right? And we are maximizing V, maximizing this thing, because V is a singular vector, the top singular vector of A minus AK. So this needs to be maximized. And the maximum is attained when sigma k plus 1 is the highest of this lot. So Ck plus 1 is 1, right? All the weight should be put on the highest. Okay? The rest are 0, and therefore that's true. Okay? And then finally, AK is the best rank K approximation is what we'll prove. Okay? So for B of rank K, I want to prove that A minus AK, B is no better than AK. Okay, B is worse than AK in spectral. But now we put a 2 there, right, instead of F. Instead of Frobenius norm, we put a spectral norm. Okay, so if rank of A, so first case, if rank of A is K or less, it's trivial, because then A minus AK is 0, right? AK takes away the top K terms of A. So if the rank is K or less, then we take away everything. Okay, so 0 is, of course, less than or equal to anything like that. That's non-negative, so nothing to prove. So we assume that the rank of A is greater than or equal to K. So A minus AK, spectral norm, we already know that. We knew that from the last slide. Okay. Now I take the null space of B. It has dimension at least D minus K. That's because the rank of B is at most K. So the null space is dimension at least D minus K. Null space, so let's say D is smaller than N. So D minus K. Dimension counts imply, now there's a vector in the null space of B, which is also in the span of these. So why is that? This has dimension D minus K. This has dimension K plus 1. So if I take 2 subspaces, the dimension adds up to more than D. There's always a non-zero vector in the intersection. Okay, I mean, this linear algebra that you should prove, right? The dimension together is more than D. If it's D or less, this need not be. Right? So if it's D, for instance, the first subspace could be the first unit vector. The next one could be all the other D minus 1. The dimensions add up only to D. There's nothing in the intersection. Nothing non-zero in the intersection. 0 is the only thing, right? But if it's D plus 1, you have to prove that there's somebody in the null space. So maybe I won't prove that, but you certainly, I mean, that's just a basic linear algebra fact. You can check that that's true. Okay. Now you scale Z to be of length 1. I can always do that and still be in the subspaces. Now what can we say with Z? So A minus B I'm trying to prove is not too small. So it's bigger than at least what Z does to A minus B, because this is spectral norm, right? This is the max over all vectors. Certainly is greater than or equal to what happens with Z. Now BZ is 0, so this is just equal to AZ. Okay. Now AZ, Z belongs to the span of the first k plus 1 singular vectors of A. So AZ, I can write again this way, and I just did the dot product squared. Now why is this? So this is the length squared. These are scalars, right? And these are orthonormal. So you just take the sum of squares of the components along UI, UJ rather, I guess. No, it's UI. Okay. So you get that. And that's equal to sigma I squared Vi transpose Z. Z is only in the span of these, so I go only up to k plus 1 there. The rest don't count. That's greater than or equal to. Now, I equals 1 to k plus 1. The sigmas are decreasing, so the least of them is sigma k plus 1 squared. It comes out, and you get that. And that's equal, this is 1, because this is the length of Z. Right? Z is in the span of these things. So I took all its components squared and added. So you get sigma k plus 1 squared. Okay? So I proved that in the spectral norm, that's the best. So that took us the most work. So AK is the best rank K approximation to A in both Frobenius and spectral norm. So this is the main reason SPD is so useful, right? So you can find most times optimization problems are not solvable in polynomial time. They won't be hard. But this is an optimization problem we can solve in polynomial time. Okay. We can find the best fit subspace. We can find the best rank K approximation today in both these senses. Okay, so I think I ran out of slides, but what I'm going to do is probably do preview of a power method on the board. Unless there are questions or discussion, we can take a 2-minute break to see if there are anybody has any questions. So this works, I think, for all unitarily invariant norms. Shatter norm is not clear because you get powers higher than 2, so Pythagoras and everything is not true. So, but unitarily invariant norms, this holds.
So how hard is it to, I want to using this proof technique, right? Now suppose I say there are two matrices, A and B.
Right.
And I consider new matrix C. C equal to A plus B. And I want to see the matrix norm, the true norm of C minus A.
Yeah.
In terms of B, right?
So perturbation results you want. Okay.
Is it?
That's a good point. Yeah. So I didn't. Yeah, I should have done some perturbation terms. Right. So here is the kind of. Okay, let's erase this and. Suppose I want sigma k of A plus B in terms of sigmas of A and B. What can I say in general? I mean, I can say good things for specific matrices, but what can I say in general? Okay. Unfortunately, the only thing we can say in general, this is less than or equal to sigma k of A, but here we have to put sigma 1 of B, for instance, right? So that is true, right? Now, why is, so you prove these kinds of, this, anything like this, you prove by taking the kth singular vector of one of these things, of either A or A plus B, and yeah, so I want to prove this is greater than or equal to, so I take the singular vectors of this, A plus B, singular vectors, so UT, VT transpose. And then I argue that sigma k of A I have a suspicion I may not be able to prove it on the spot, but it is true. This inequality is true. Okay. I do pay for, this could be very high. It would have been nice if I said sigma k of A plus sigma k of B. It's not true in general. Okay. So this is all I can say, right? Maybe I won't actually prove this, but you could ask. So suppose B is very small. B is noise, right? How much do singular values get perturbed? That's one thing you could ask, right? So there is something called the Hoffman-Wieland inequality, which is a very nice inequality and that says the following. Sum over, let me risk writing this, sigma k squared of this minus sigma k squared of A so I'm going to try to say that this is less than or equal to this. I could be wrong, and I think I may have to take a square of this and add and get a fourth power. So the Hoffman-Wieland inequality is often stated for eigenvalues of symmetric matrices. And you get singular values just by taking symmetric matrices A plus B times A plus B transpose. So don't worry for the moment about the exact inequality. You can look it up. What the idea is that if B is not very big, then I don't change the singular values very much, right? Which is what you'd expect. That's what this is saying. Okay? So the right-hand side depends on B. If B, for instance, B is 0, of course you should get 0 on the other side. It is. This is 0. This says it's less than or equal to. Okay? That's one kind of theorem that's nice to know. So I want to perhaps point out another kind of theorem since we asked for perturbation results, which is what happens if you have a random matrix. So first, if you have a random symmetric matrix, what does that mean? That means Aij j greater than I, or IID, let's say, normal 0, 1, and Aij j less than I by symmetry. Above diagonal entries or independent random variables, I want the matrix to be symmetric, so below diagonal entries better be equal to the above diagonal entries, right? Corresponding ones. And the expected value of each entry is 0 and the variance is 1. Right? Now, we know that then the length of AI squared, sum over all ij, that's the Frobenius norm of A squared, and I want the expected value of that, it's a random variable. So the Frobenius norm of A squared is just the sum of the squares, right? The expectation can go n, it's just a sum. Expectation of the sum is sum of expectations, right? Even independence is not required here. So these expectations about diagonal, well, I didn't say anything about the diagonal, so let's say that A, I are all 0. They could also be normal 0, 1. Maybe I'll just make AII is also normal 0, 1, excuse me. They don't matter too much. Okay. So each entry has variance 1, so you get n squared. Okay. And we saw that this is the sum of the singular values. So that implies sigma 1 squared of A is less than or equal to AF squared, which should be less than or equal to n squared, Cn squared with high probability. So why is that, right? It's the Frobenius norm in expectation is n squared, only in expectation. But the sum of many independent variables, so it's not going to be greater than Cn squared, right? We saw that sum of independent variables, the tail bounds are good. So this won't be very large with high probability. This stands for with high probability. Right? And so sigma 1 squared is less than n squared. In general, sigma 1 squared can be, if A is rank 1, sigma 1 squared equals AF squared, right? If A is rank 1, sigma 1 squared A equals A squared. That's true. But in fact, for random, this setup, that's in general. In this setup, we can, the theorem is that with high probability, sigma 1 squared of A or sigma 1 of A is less than or equal to, let's see, I think it's root 2 plus epsilon times root n. Or maybe I should just say is asymptotically about root 2 root n. Okay. Now, what's nice about this is hard to prove. This I'm not going to prove here, right? The reason it's hard to prove is that this is the max over all x of AX, right? So to prove this, you must prove that for every one of these infinitely many x, you must prove for every x that's true, that AX is less than root 2 root n. So that's not the subject of this lecture, so I won't be able to prove that. But I want to point out one thing before we go on. And the one thing is the length of one row of A is itself as large as root n. So let me do the expected length squared of one row of A is equal to sum over j expectation of AI squared, Aij squared. These are all ones. That's n. So one row is as long, singular value, it says, is at most the length of one row times the constant. Okay. Now that's quite striking, right? That won't be true for arbitrary matrices. Why is that quite striking? Because of the following. Sigma 1 of any A is greater than or equal to the length of A times the first row, okay, written as a column, that's equal to the length of A1 squared, greater than or equal to. So I take the first row dot product with this, right? So that's the length squared, the square. Sorry, so I have to divide by A1, right? I have to make unit length vector. So certainly it's true that sigma 1 is trivially greater than or equal to this. I'm even ignoring the contribution of the other rows. The other rows may make a good dot product with A1 too. Okay. So this is telling you that the rows are uncorrelated, right? In a random matrix, I take the first row, I get about root n. I really almost get nothing from the other rows. I only get a constant factor more. So it's as if the rows are, in a sense, uncorrelated. And they are independent random variables. So it for one thing says, this thing implies the rows are uncorrelated. Okay. So random matrices are one extreme, but SVD is used for totally unrandom matrices in practice. So let's say what that is. So typical use of SVD, so this again I was going to go over next time, but I'll try that now. Typical use of SVD is principal component analysis. And principal component analysis, or PCA, says replace A by AK and just compute with AK. This is only good if the first K, if the truncation leaves very little error. Now we just saw that the error it leaves is, in spectral norm, is the K plus first singular value. So if this is much smaller than, let's say, sigma 1, this is an interesting thing to do. So in practice, you use this a lot for matrices which have this property. So useful if sigma k plus 1 is much, much smaller than sigma 1. But for random matrices, that's not true, because sigma 1 itself, for a random matrix, sigma 1 itself is order root n. Yeah? Sigma 1 is order root n, and the sum of the squares of all of them is n squared, right? That's a Frobenius norm, which is order n squared. So sigma 1 is basically just about the average in square, right? So sigma 1 squared is more or less within a constant factor of the average sigma t squared. So there are n of these, their total is n squared, the average is n in square, and sigma 1 is only about that. So it's far from having this inequality. So this and this are far. So if it's a random matrix, you should not use PCA, right? The assertion is, in practice, a lot of matrices have this property, that sigma k plus 1 is much smaller than sigma 1. Okay, that's why you use PCA. Sorry? Is it easier for random matrices? Actually, I don't know. No, I don't know that. I mean, like, I don't know an algorithm which for random matrices is easier or faster, right? In fact, there's a vague folklore that is harder because the gaps are small. So random matrices are often thought to be the hardest, sort of. Yeah, so it may be that. So for instance, one conjecture would be that if I pick a random subset, there will be a singular vector just in the span of those. Yeah, I think some things like that might be true. I don't know proofs of those things. The numerical iterative methods, which don't sample, certainly for them, random matrices are thought to be hard because the gaps are bad. But the suggestion, maybe that's what you're making, is that right? If I pick a few random rows in their span, I should have a good singular vector. That's possible, yeah. I don't know proof that something quantitative works like that. So I will stop here because I don't have anything more to say, but if on Monday we'll come back and do the power method. I didn't do the power method, but yeah.
Sorry, is the agenda there to cover your consequence of this multiplication paper into the eigenvalue computation?
Yes, that is the SVD computation. So it's a little more complicated. Length squared sampling, SVD, that was one of the topics I put up later, but maybe I will move it up, come to think of it. But it's complicated, but it's more complicated than multiplication or compressed representation.
And as part, if I read a paper at that point, the often white is the first time I heard, so looking for the proof.
Okay.
So you have to do the proof, right? If you're doing a paper?
Yeah, so, okay, so maybe we'll move that up in the agenda. But first we'll do the power method because, I mean, it's nice to know the power method. And, Okay, so first we'll do the power method, and then we'll, and Gaussian mixtures, spherical Gaussian mixtures. Those are both nice to know, and then maybe we'll do SVD with length squared sampling.